Number 26 is the reason why I have two types of systems. What are the two types of systems?
Objects and reaction.
Yeah, object and reaction. An object just stays there as a permanent object. And so if you have an object and it just stays, the only thing you can do is you can warm it up or cool it down. So that's the object. And the other one is a reaction or process. Now, the reason I divide it this way is because a reaction or process only lives for a short period of time, and then it's gone. And so if you're looking at the reaction between HCl and sodium hydroxide, once the reaction is done, then there's no more system. The system disappeared. And so the only thing that's producing heat here, this is going to be Q the system, which is going to equal Q the reaction, which is equal to delta H of the reaction, or delta H of the amount times, amount times delta H. Once this reaction's done, then there's no more system. So it reacts, it produces heat. Everything that's left over is now considered surroundings. So this water and this salt wasn't originally in the surroundings. But now that's what's left over, and it's going to be treated as surroundings. And so the system itself is just this part here. And then it's going to release heat. All that heat's going to be absorbed by everything remaining. Everything remaining is the products from this, plus the styrofoam cup, plus whatever else. In these problems, they don't worry about the cup here. Assume that no heat was lost to the surrounding air and that the solution produced. Yeah. So they don't really worry about this. Actually, they give us the specific heat of the solution that's produced. The solution that's produced is the surroundings. So this is the surroundings. And they're saying, we're not going to lose any heat to anything else. So that's our surroundings. That's the leftover stuff from our system. And so this is an object, and this object is just going to warm up. And so this will be Q, the surroundings here. And so Q, the system, is equal to minus Q, the surroundings. Minus Q, the surroundings, is this saltwater solution. And we're going to start off at whatever temperature initial, and then this is going to heat up. The sodium chloride aqueous plus H2O final. And so we figure out how many grams because they give us the specific heat for that salt solution of 3.98. So it's a little bit lower than pure water.
So it's for every problem that it's a reaction or a process object. Once you find the Q of the system, you can then move and switch to the negative Q of the
Yes. Yeah. Right. And so what Colin said is once you find this, then it automatically switches to this. That's correct. Okay, any other questions? No? All right, today I have the computer lab scheduled. So we're going to do some graphing there and then some spreadsheet work. All right, there's one other thing I want to talk about. We're going to do one standard scientific paper or report this semester. And I think we'll do the sulfate. I was thinking we'll do experiment 2, but probably the sulfate will work good for this. So we're going to write a scientific paper or report for sulfate analysis experiment. And the scientific paper report is just going to have a format, a special format. And the special format depends on what journal, but most journals have a similar format to this, so we'll just stick with this this format. This comes from the ACS, which stands for American Chemical Society Style Guide. It's from 1986. It's an old one, but it's still good. So the first thing is, what is the audience? Well, the audience here is just the standard audience. Sometimes it's a specialized audience, but if this is a standard audience, then we don't do anything special for this. So they talk about writing style here. You can read through this. And now let's talk about the components of the paper here. And so it's just going to be formatted in a certain way, and then there's going to be some additional description of what you did, and also how you analyze things. And so the first part of the the paper is the title. Normally in a title, you want it to contain a lot of keywords that make database searching a little easier. But for us, we're not going to worry about it. So they choose terms that are specific as text permits. So vanadium iron alloy is better than a magnetic alloy, etc. But you could have magnetic in there. That's a good keyword to throw in the title. So you can read through this. So we'll just have some simple title. The next section is the byline and affiliation. The byline is just the names of the authors. So if you worked in a group, you'd have all the members of your group will be authors on this paper, and you'll just turn in one paper. If you worked alone, then it would just be a single author paper. If you worked alone and you want to work with somebody else with the paper, that's fine too. We're going to go through and work through this paper together. Anyway, it depends on the journal. Some journals want the full first name. Other journals just want the initial. And so you have to look at the particular journal's requirements. But whatever you do, just be consistent. I don't care if you do first initial, last name, or first initial, middle initial, last name, or first name, middle initial, last name, etc. But you should be consistent throughout. We don't include professional or official titles or academic degrees. So you wouldn't say, like high school diploma or whatever here. You just the name, and you can't tell what degree they have. But you can tell where they work, because the affiliation is where they work or where they're going to school. So your affiliation would be El Camino College. That should be it. The affiliation should be the institution where the work was conducted. You don't have to put the address in. You could give the current address as a footnote at the bottom of the page, but it shouldn't be in the byline, address and phone number, just the name of the institution. So we have the title, then we have the authors and the affiliation. The next section is the abstract. Does anybody know what the abstract is? First two? Mm-hmm. Yeah. It's a one-paragraph summary of the entire paper. Most people have too much stuff to read and not enough time. And so most people will only read the abstract. Actually, most people will only read the title. And then you'll have some people that will read the title and the abstract. But excuse me, the abstract should contain your basically the findings, the principal findings of the paper. And so, in other words, we're doing a sulfate analysis on an unknown. And so a person reading this abstract should be able to find, what percentage sulfate was contained in your unknown samples. And so you need to give the final result or the final conclusion or the key findings in the abstract in one paragraph. And so most people will just read the abstract. And if they're interested in the fine details, they'll read the whole paper, but they should be able to get everything out of the abstract here, as far as the important findings. So in the abstract, you should briefly state the problem or the purpose of the research when that information is not adequately contained in the title. Indicate the theoretical or experimental plan used. Okay, we're using gravimetric analysis. Accurately summarize the principal findings and point out major conclusions. Include chemical safety information when applicable. But do not add to this. Like, for example, there should be no figures, there should be no tables. Then you shouldn't have a lot of additional. I mean, if people are more interested in the work, then they'll read the entire paper, which should have a detailed, the detailed results and detailed discussion of the experiment. Okay, the abstract should be concise and self-contained. So typically no more than a paragraph. Our abstract will only be a paragraph long. Do not cite references, tables, figures, or sections of the paper. It should be completely self-contained. You shouldn't have to search anything for this additional information. Okay, that's the abstract. We'll talk more about that later. Okay, the next section of the paper, let's see, is the introduction. So the introduction is, it could be historical, and puts them what's been done in the past for this particular system, or it could be things that are of interest today for this system. The introduction, you could put whatever you find significant or interesting about this, what's been done in the past and what your plan is for this study. So a good introduction is a clear statement of the problem or project and why you're studying it. And so this one you could put in whatever. So for example, you probably don't know much of the history of gravimetric sulfate analysis. I mean, you could Google search it if you want, and then look, what type of, or who started, gravimetric sulfate analysis, or who started gravimetric analysis. So you can have a little historical perspective. Gravimetric analysis is a technique that's been used for, hundreds of years. And in this experiment or this paper, we're applying it to determining the sulfate content in some unknowns, something like that. Or it could be related to sulfate. Why would anybody care how much sulfate a sample has? Is sulfate good for anything? No. Does anybody care about sulfate? And so what you do is you can do a search and see, if there's something interesting about sulfate and why somebody would want to do a sulfate analysis in the first place, or etc. So just some introductory remarks for this. If you talk about some historical work, then usually demonstrate the continuity from previous work to yours. So this is another step, or It's hard for us, you know, this is just an application. And so that would be the continuity there. Okay, after the introduction, which basically tells the reader, you know, what's interesting about this work and why it's relevant, then we go to the experimental details. Or if it's a theoretical paper, you know, the math. But ours is experimental. The experimental details is also called experimental methods. It's also called the experimental section, or it's just called experimental, which is not written here, or materials and methods, or methods and materials. They're all the same. And what this is it's kind of like the recipe. Let's say if you're going to make a cake or cookies or whatever, you have a recipe for doing this. You add this. Actually, I'm going to post this on Canvas. I forgot to do it. I was supposed to do it last week. So you have a recipe for making cookies. And so it says add this much sugar, add this much flour, this many chocolate chips, this many almonds, whatever you put in there. But the experimental section is not the recipe. The experimental section is what you actually did. Let's say you like a lot of almonds, so you put more almonds than the recipe called for. But you know, you aren't going to write the recipe here. You're going to write the recipe that you actually used and how you did it. And so the experimental section, this is like the nuts and bolts. You know. So for example, what did the or actually, how many grams of unknown did you use? You know, what did it look like? The unknown was a white powder, and you weighed out such and such grams. Now, how much detail you want to get into? We have to use some, like, for example. Do you want to say that you walked over to the oven and you were handed a beaker that contained an unknown sample that was in a weighing bottle, and then you walked back to your desk and grabbed a desiccator and then walked back? No, you don't want too much detail, but then you don't want too little detail. The amount of detail you want is so that somebody who reads through the experimental section can repeat it in pretty much the same way you did. So for example, if you used a 400 milliliter beaker, was that really critical? Could somebody use a 600 milliliter beaker, or could somebody use a 250 milliliter beaker and get the same result? They probably can use any size beaker they want as long as it doesn't overflow. And so that's not so relevant. It's not so relevant if you use a 400 beaker or 250 milliliter beaker. So you can leave that out. The other things you could leave out are, well, did you weigh the weighing bottle? You know, and in fact, we could leave all that weighing stuff out. All we need to say is how many grams of sample we have, because we figured that other people can figure out how to weigh things on their own. They don't need step-by-step instructions on how to weigh samples. And not only that, we didn't even follow the procedure, because the procedure called out for weighing the sample with the bottle and then tapping some of the sample in and then re-weighing the bottle with the remaining sample and then subtracting the two. Did you do that? No. And do we need to even talk about that? We don't even need to talk about that. We just say, you know, we got this many grams. They can weigh however they want. If they want to weigh the weighing bottle, fine, let them weigh the weighing bottle. You know, you can weigh things in different ways, and it doesn't really matter. So certain details we can leave out, but other details we should include. The other details were, how much water did it take? Did the crystals dissolve easily, or was it tough to dissolve? That is, did you have to get a stir rod and crush the crystals to get them to dissolve, or did they pretty much dissolve? Did you have to heat it up to dissolve? You know, we need other details like that. So that should be in there. Okay, so what you're going to do is you're going to give enough details here of how you did the procedure so that somebody else could redo it. And so that's the experimental details. Experimental details are a little bit more than the procedure. The procedure is just the recipe. What you actually did is what we want. And that's called the methods and materials or experimental section. All right. In the experimental section, we really don't talk about the chemistry unless there's some kind of precautionary handling procedures. Let's say there's a potentially hazardous step or something's quite toxic, then you want to talk about some of the chemistry here. But otherwise, it's just how many grams, how many milliliters, you know, what happened when you mixed it, this kind of stuff. Okay, once we're done with that, then we go to the results section. Sometimes people combine the results with the discussion. And so what's the difference between results and discussion? We keep these separate. And the reason we like to keep them separate is the results are just the experimental facts, you know, the factual observations from the analysis. There's no interpretation here. So results would be something like this, you know, 0.xxxx grams of unknown were used in trial 1, etc. And then point y grams of white precipitate was weighed, you know, at the end after drying. You know, how long you dried it, I should be able to find that in the methods section or the experimental section. But I wouldn't say something like this. I wouldn't say, you know, 0.y grams of barium sulfate precipitate were obtained, because I wouldn't say barium sulfate, because is that white precipitate really barium sulfate? You know, are you convinced 100% that white precipitate at the end of the experiment is 100% pure barium sulfate? Is it? Well, the first thing is it barium sulfate? You know, how can you prove to somebody that white precipitate at the end is barium sulfate? Well, in the results section, we don't even say it's barium sulfate. We just said it's a white precipitate. Now, how can you prove it's a white precipitate? Because you just look at it, it's a white precipitate. And it's easy to convince, you know, you have somebody look at it and then they see it's a white precipitate. There's no convincing there. But if you're saying that that's pure barium sulfate, and hopefully it is pure barium sulfate, you know, and hopefully it's not grossly contaminated barium sulfate, and hopefully it's not something else other than barium sulfate. But we need to convince our reader that it is, and that's what we do in the discussion section. And so in the results section, this is just the facts of the experiment, the facts you can't dispute. That's how many grams you got. You know, maybe it's an error, but that would have been an error there in a measurement, not an error in analysis. Whereas the discussion section takes this and then interprets it. You know, we have this. And so the first thing is, you know, how can we justify that white precipitate at the end is pure barium sulfate? One, how can you justify it's barium sulfate? Well, here we're going to have to talk about the chemistry of this, right? For example, could it have been barium phosphate? Or maybe barium carbonate? Yes? How do you know it's barium sulfate? And so we're going to talk about that here in the discussion section. And the next thing is, how do you know it's pure? Maybe it's a mixture, barium carbonate, barium phosphate, barium sulfate, and a whole bunch of other stuff. Or maybe there's some contaminants of barium chloride and hydrochloric acid. How do you know it's pure? And so in this, then we're going to do that. We're going to go through and explain, you know, and describe in more detail why we think we got number one, barium sulfate, and number two, why it's pure barium sulfate. And it's a tougher job for you guys because when I was working in a research lab, I would think of this, but it's easy because what I do is I just take that white precipitate we formed and then I'll put it in this big machine, which is called an X-ray diffractometer, and then just blast it with X-rays. And from the diffraction pattern there, from the scattering, I could see, how much barium sulfate is there. And then I could look, because it's like a fingerprint, then I could look for contaminants in there, impurities. And it's quantitative, because of the photons. It's quantitative, so you can determine if there are impurities, what they are, and how much of them you have in there. This is something that we do usually for anything we make. For anything we make, we want to know, is it the stuff we think it is, number one, and number two, how pure. And therefore, let me backtrack a little bit. Therefore, when we're in the experimental section, we talk about the chemicals we use. Because, that can have an impact on the purity of your product. And the chemicals that we use, usually you buy them, and you can buy the expensive stuff or you can buy the cheap stuff. Usually the expensive stuff is high purity, and so we give it different grades. Here at El Camino, most of the stuff we buy is the cheaper stuff. The cheaper stuff is the technical grade stuff. The technical grade stuff is like 95% pure, 5% impurities, And so there's things like technical grade and things that are pharmaceutical grade, things that are analytical grade, and food grade. What do you think is the highest purity? Analytical grade is the highest purity. That you're going to be spending a lot of money for, because if it's not pure, they purify it. And so this purification adds extra labor and expense. And so the analytical stuff is expensive. What do you think is at the bottom end? Food grade. And surprising, some of these chemicals I read, 3% lead. Well, 3% lead, are you sure you want to use that? There's some chromium, lead, some other heavy metals. I think, wow. But fortunately, these they put in small quantities, and then there's some standards, FDA standards or whatnot, for how much lead can be in there. And so it's below those standards, but it makes you wonder about if you use analytical grade, the food would be terribly expensive, just way too expensive. So anyway, in the experimental section, we need to say the source of the chemicals and the grade. We don't know, because the source of the chemicals, barium chloride, hydrochloric acid, we just got from the stockroom. And so we call those stock solutions. We use the stock solution of barium chloride from El Camino College stockroom, and the stock solution of HCl. Those are common. Stock solutions are different than standard solutions. What's the difference between a stock solution and a standard solution? Well, what is a standard solution, first off?
Does it have the same criteria as just like a primary standard?
Right. Does it have the same criteria as a primary standard? Yeah. Not exactly the same. Because standard solutions are usually measured by volume, whereas primary standards are usually measured by mass. Mass is more reliable. But measuring mass of solutions is a pain, because you got to seal it, you got to watch out for evaporation and this kind of stuff. So usually primary standards are at a higher standard, more restrictive standard than standard solutions. And so if you had a standard solution of 6 molar HCl versus a stock solution of 6 molar HCl, then you treat those differently. A stock solution of 6 molar HCl, you have some stockroom technician there doing a solution dilution, mixing it up. Do you think they're going to be extremely precise? No, they don't want to waste a lot of time. They're just going to mix it. And it's going to be close to 6 molar, maybe 5.5 to 6.4 molar. That's good enough, right? But a standard 6 molar hydrochloric acid solution will be right on 6 molar. It should be 6.000 whatever, however many decimal points you can get out of that. I mean, decimal places you can get out of that. And so standard solution is going to have an accurately and precisely known concentration, whereas stock solutions are just made for general laboratory use. So these are all stock solutions that we're using. The unknown, what did the unknown look like? That's a white solid. It was a water-soluble white solid. All right, so in the discussion, we don't have an X-ray diffractometer. We don't have an X-ray diffractometer. What are some other ways you can prove that white precipitate at the end of this experiment is barium sulfate? Can you think of any other ways that you can prove to me that was barium sulfate? Other ways, like experimentally, we can do it by the chemistry. We talked about the chemistry. We talked about the chemical reactions. We talked about why we think there aren't going to be interferences contaminating our final precipitate, right? And we talked about why we think it's clean, 100%, because how we cleaned it, this kind of stuff. But are there other ways to prove that is actually barium sulfate, like an experimental, rather than going through the chemistry of it? Well, one, it's white, and barium sulfate's white, and so is that enough? Barium sulfate's white, the final precipitate's white, they're both white. Is that enough? No, but it's a piece of evidence. The more evidence we have, the better. And so what else can we use in addition to that?
Check solubility in water.
Yeah, we could check solubility in water. It's insoluble, but that's the qualitative solubility. We can go to quantitative solubility. Let's see if I have that here. You just go to Wikipedia for barium sulfate and check the solubility. It's insoluble, but it's not infinitely insoluble. In other words, a little bit will dissolve. And actually, that's more than a little bit. That's almost a quarter gram. A quarter gram of barium sulfate will dissolve in 100 milliliters at 20 degrees C. So you don't want to be washing with too much water. If you're washing, let's say I use 400 milliliters wash. If I use 400 milliliters of wash, then I could potentially lose, not 1 milligram. Actually, yeah, this is only quarter milligram, sorry. I could potentially use 1 milligram. Well, is 1 milligram all that much? No. So even if I use 400, but the thing is, we don't want to use too much because we'll lose a little bit each time we wash. And so we don't want to use too much water, but then again, we don't want to use too little water because if you didn't wash it enough, then some residual contaminants could still be there. And those residual contaminants will mean that it's not 100%, but it's something lower than 100%, right? And so, so how do you know you used the right amount of wash? Well, you did some procedures to figure out if you washed it enough. Okay, once we have that, then we can measure the solubility. That is, just get 100 milliliters of water and figure out how many grams dissolved. And if you come out to 2.2448, then that's another piece of evidence that, yeah, that is barium sulfate, or it's looking like it's barium sulfate, right? And so we could use solubility to help identify it. Is how many other things have a solubility of 0.2448? Although I don't know if you're going to get it to that number of sig figs, And I don't know how many experiments that's based on. Is that based on a whole bunch of people doing it, or just one lab doing it? And if one lab doing it is doing it, then there could be random error associated with it. We want lots of labs doing it and getting the same number. If lots of labs, let's say 100 different labs did it, and 100 different labs got the same number, then you know that's a reliable average number there, a reliable number. Is there anything else we could do? The odor? Yeah, it should be odorless. The color? And so that's 3 pieces of evidence. Anything else we could do? We could try melting it. And melting is very common. And in fact, melting, do you guys remember what I said about melting points? If you have a sharp melting point versus a broad melting point, which one is more pure?
Sharp.
The sharp melting point. That's high purity. So we could try melting it and see, does it melt right on 1580, or does it melt over a range of temperatures? If it melts over a range of temperatures, that's a clear indication that it's not pure. But if you look at this melting point, it's at 1600 degrees C. You know, do you know any ovens that'll get that hot? No. That's 2,880 degrees Fahrenheit, almost 3,000 degrees Fahrenheit. You're not going to melt it. This won't melt. Although, in our research lab, we had an oven that went to 1600 degrees C. So potentially you could have melted it. But that oven was made out of platinum. At least the heating element was made out of platinum. It was probably a $100,000 oven now. But this is not going to happen. But this might happen. This is not too hard. Anything else we could do? We could try measuring the precipitate's density. Because if you look at the density is 4.49, which is fairly high. That's 4.5 times more than water. You know, how many other things have a density of that? Well, maybe there are other things that have a density, but what we do is we try to get more and more observations, more and more evidence that this is barium sulfate. So we can use the density. Anything else? We want quantitative things. Like these are qualitative, insoluble in alcohol. That's not so quantitative. Here are some other things that are quantitative. Magnetic susceptibility. But you need some instrument to measure that, which we don't have. And we could do the refractive index, but you need a single crystal to measure the refractive index. We don't. We have lots and lots of tiny crystals. We can't even see them individually. If you get a microscope, you might see an orthorhombic. Orthorhombic has a certain shape to the crystal. But what we can do is we can use some properties, some physical properties to help us identify that it is. And we've already talked about the chemical properties as well, some of the chemical properties. Another thing you can do is you can do heat capacity. I don't know if you want to do that, but you treat your barium sulfate precipitate as an object. And so get some hot water and see how much heat is absorbed by the precipitate, how much heat is absorbed by the styrofoam cup, the thermometer, and the lid, and the outside environment, the calorimeter we call it. And so we can do a calorimetry experiment and measure the heat capacity. Should be 101.7 joules per mole Kelvin, which is fairly high. Water is only 4.18, and that we consider high. Okay, we aren't going to measure that. We aren't going to measure that. Etc. So in the experimental section, we usually have, the experimental being the methods and materials. We also include words about the toxicity of these. Like here, barium is a heavy metal. So you don't want heavy metal poisoning. But when I went for a CAT scan, for my GI tract. They gave me a barium meal, which is just a pasty liquid. It just tasted like a chalky liquid of barium sulfate. And so you drink the barium sulfate, and then they can image your GI tract with X-rays. Heavy metals are good at absorbing X-rays, like lead, barium, etc. But it's not so toxic in this form because its solubility is so low. So even though I drank a whole bunch of barium sulfate, I wasn't worried about dying. If I drank barium chloride, that's a different story. Barium chloride would be much more toxic than barium sulfate. Why?
It gets rid of the chloride.
Yeah, because barium chloride's soluble, barium sulfate's insoluble, so it gets rid of the chloride, and then the barium can cause damage to proteins, like lead does. And so I drank a suspension of fine particles in a thick milk-like solution. And it was sweetened. They added, I forgot what flavor. I think it was apple flavor or something to make it more palatable, but it doesn't really have much taste. I mean, it doesn't have any odor. Okay. Anyway. So, do we have time to do any of this? No. And so we're just going to use arguments based on the chemistry that we're describing to convince the reader. And so the discussion section is the most important. This is your analysis. Now, what happens in science is this. We keep the analysis separate from the facts, the factual observations. And the reason is because science is continually progressing. As science progresses, think back like 200, 300 years ago. And, 300 years ago, how they did medicine back then, I think, where, since I just had some blood drawn, I was just thinking about this. Where if you had some kind of disease, they would cut you and let you bleed the disease out. Do you think that was very effective way for treatment? No, disease. And so things change with time. The disease might not change, but how you analyze, how you treat it could change. And so the same thing here. This happens, and sometimes this happens very quickly. Like, for example, one group publishes a paper interpreting the results, and then another group, at some other institution, reads that and disagrees. They say, these guys haven't convinced me at all. And so what they did was they scratched their discussion and then took their data and then analyzed it differently. And so the paper, often you'll see this title for paper, Reinterpretation of So-and-so's Experiment. And so the discussion can change, but the results should never change, and this is why we separate them. But for short papers, sometimes they're written together. And so, did I talk about the results? So the results are just how many grams. Probably in the table is the easiest way for us, for our experiment. And then we'll have the discussion. And eventually, at the end of this discussion, we should convince the reader that this is indeed the percent sulfate that is in the contained in the unknown. All right, the conclusion usually comes at the end of the discussion, so we don't have a separate section here. If you have already presented your conclusions in the discussion section, you do not need a separate section for them here. And so we're not going to have a conclusion section. Instead, we're going to add something at the end. Now, a conclusion is not a summary. A lot of people will start the conclusion. In conclusion, we talked about this, this, and this. We're not going to summarize the entire paper in a conclusion. The abstract does that. And so the conclusion is, where do we take it from here? What are some other steps? What are some shortcomings of this, and how could we correct those shortcomings? Or were there some mistakes? In other words, it would be like, what you would like to do next if you had the time and budget to do it. Or how could you improve the procedure that we did? Are there any ways that you can think of to improve this? Summary is also not necessary. Summary is unnecessary in short papers, less than 20 pages. So we're not going to do a summary. So the paper is pretty much going to end with the discussion section, and the conclusion is going to be tacked on as a sentence or two or three at the end. the discussion. An acknowledgement section. This just acknowledges who funded the research, or if there are other contributors that weren't listed as authors. And so maybe somebody helped you with something, but they're not co-authors. They didn't do enough work. And so you just list their contributions here. Who funded this would be like the state of California funds El Camino. And then we have references. The style for the references, they could be treated as endnotes or footnotes, either way. But the style depends on the journal. You could just use whatever style. I don't really care. There is a chapter on references in this as well, so you could use that format too. And then there could be special sections. Let's say you have pages and pages of calculations or pages and pages of data tables. You don't want to insert those in the main body of the paper because it'd be too long. So you attach those in the appendix. And so appendix, or it could be a glossary, list of symbols, whatever. Just extraneous stuff. And so that's it. So we'll start working on this. And since this is the first one for many of you, we'll do it together for the most part. Okay, this goes on to talk about presentations. Book chapters, reviews, etc. But in chapter 2, there's grammar, style, and usage. And so this is worth reading as well. And this is specific for science here. So they'll give you a lot of examples. Like incorrect. Growth and isolation of M13 virus was described. Correct. Growth and isolation of M13 virus were described. Something like that. So you can read through this. This gives some common grammatical errors, which I should read this many times as well. I've probably forgotten a lot of it. Okay, any questions on this? So you're going to do the calculations on the sulfate analysis report sheet, and then it asks you for one final calculation. The one final calculation is the average deviation from the mean for your trials. We're not going to do that. They're asking for the average plus or minus the average deviation from the mean. The average deviation from the mean is not the standard way of reporting averages. The standard way of reporting averages is by using a confidence interval. Confidence interval. And the one that's most commonly used is the 95% confidence interval. So we're just going to call it the 95% confidence interval. What the 95% confidence interval tells us is something like this. Let's say student A had 3 trials. The first trial, they got 0.5 grams per liter. They're trying to measure the density of water. And in the second trial, they got 1.0 grams per milliliter. Per milliliter. And in the third trial, they got 1.5 grams per milliliter. And they average it. What's the average of this? 0.5, 1.0, 1.5, 1. And let's say at this temperature, the true density of water is 1.0 grams per milliliter. And so what would you say? They're right on. Their average is right on.
Their average is right on, but their data is...
Yeah, their data is spread out all over the place. Let's compare that to student B. Student B, let's say, got 0.9 grams per milliliter in trial 1, 1.0 grams per milliliter in trial 2, and 1.1 grams per milliliter in trial 3. And if we average that, what would it come out to? 1.0 grams per milliliter. So would you have equal confidence? Because they both got the right answer. They both got 1.0 grams per milliliter. Would you have equal confidence in student A versus student B?
No.
Let's say student A is going to do some surgical procedure on you. Well, they both got the right answer. They're both equally adept, would you say? No. I'd have a lot more confidence in student B. And so we need some way of showing this. The way of showing this is by the 95% confidence interval. And so the 95% confidence interval does this. The more measurements one takes, the more confidence we can have in the average. So if somebody measured 3 versus 100, you know, an average of 100 data points would probably be better than an average of just 3 data points. And so the more data we have, the more confidence we could have in the average. And also, the narrower the spread, the more confidence. And so the 95% confidence interval factors in those two things. And so in order to determine the 95% confidence interval, we take the 67% confidence interval. Do you know what the 67% confidence interval is called? Or the 60+% confidence interval? Do you know what it's called? It's called the standard deviation. It's for an infinite population, but we're going to not worry about that. And so the first thing is, to get to the 95, we're going to calculate the 67%. And the 67% has a special name called the standard deviation. But in science, 67% is too wide. You know, because if it's 67% confidence we have, and this is the way we read it, we have 67% confidence that the true value lies within this range. But that means there's a 33% chance that the true value lies outside the range. And so what we do is we need a wider umbrella. And that wider umbrella is going to be the 95% confidence interval. And what that means is there's 95% confidence that the true value is in that range, and only a 5% confidence that the true value is actually outside the range. And so that's going to be wider. But anyway, to get that, it's easiest to calculate the standard deviation. And then from the standard deviation, we'll get the 95% confidence interval. We're going to do this using equations, but we're also going to do this using Excel. Excel can do this quite quickly. And so I have the data here. Let's take a look at the data in Excel. And also, we're going to be working with spreadsheets today. So I'll show you how you do this here. So here's student A. They had 0.5, 1, 1.5. Let me get the number of decimal places right. I want 1 decimal place. Actually, let's center this too. Here's student B. All right, the first thing we want to do is we want to calculate the average. So Excel can calculate the average quite easily. It's a very common formula. There are 2 ways to get the formula. One, I can use this fx here, insert function, and then I could just go to the average. There are 2 averages here, average and average A. We'll just use average here, and then click OK. And then it's going to ask me to average which numbers. I'm going to average these numbers here, and then hit enter. And the average is 1.0. The other way of getting the average, I'll do over here. Oops, I didn't want to do that. The other way is I can just type in the equal sign and then type in A, and it might come up. If it doesn't come up, I'll type in AV. Yeah, and I see it here. So I see average here. I can double click on this, or I can hit the tab key. I'll hit the tab key, that'll populate that. And then I'll get the average here, and close the parentheses. So they both came up with the same average. And so this is the average. Okay, the next thing I'm going to get is the standard deviation. I'm going to abbreviate standard deviations STD, Okay, there are two ways I can bring it up. One way is I can use the fx insert function, and then I'm going to narrow this. It's already narrowed to statistical because I was doing this. I could go to all. There are too many functions here. Or I could search it. But I'm going to narrow this down to statistical, and then just scroll down to S. When I go to standard deviation, I have several choices. I have standard deviation P, calculates the standard deviation based on the entire population, given those arguments. I have standard deviation S, estimates standard deviation based on the sample. Okay, we have a finite sample. We don't have an infinite population. We're only doing 3. We're not doing millions and millions of data here. So what we're going to do is we're just going to use the S for sample. We have standard deviation A, standard deviation PA. Let's see what those are. Standard deviation estimates standard deviation based on a sample, including logical. We're not having any logical values. Standard deviation PA, entire population, including logical and text. No. So we're going to use standard deviation S. So I'm going to click OK. We're going to get the standard deviation of our 3 data points here. And then hit enter. So my standard deviation is 0.5. So between 0.5 and 1.5, I have like a 67% certainty that the true value lies in that range. But I don't want to think, because there's a 33%, it's outside that range. And so what I'm going to do is I'm going to get the 95% confidence interval. And so here I'm going to put the 95 CI for confidence interval. Oops. Okay, over here I'm going to just, the easiest is just to copy and paste it, but I'll show you the second way. The second way of doing this is equals, and then I'll just write STD, and then I'm going to do deviation S, and then select the data here. Enter. That's it. For the 95% confidence interval, I can insert the function fx here. I'm going to go to confidence. Okay, I have 2 choices here. I have confidence.norm and confidence.t. You know the difference? The difference is the distribution, the shape of the distribution. So this is a confidence assuming a normal distribution. This is a confidence assuming a t distribution. This t distribution is called the student t. And in science, we use the student t distribution. So let's take a look. Confidence.t. Now this is using student's t. Now student is not a student in school. Student is the mathematician's name. This is coincidental. So when I do the confidence.t, the first thing it asks me is for alpha. The alpha is it's kind of weird. It's 1 minus alpha. So if alpha is 0, then that's 100% confidence interval. 100% confidence interval is going to be infinite, infinitely wide. Then we have 100% confidence. It's an infinitely wide range. If alpha is 0.5, then that's what we call the 50% confidence interval. If alpha is 0.1, that's what we call 90% confidence interval. So we can calculate whatever confidence interval we want. For 95%, we need to make alpha 0.05. So that's 1 minus 0.05 gives me 0.95. 0.95 is 95% in decimal form. And so that's my alpha there. Okay, this calculates the confidence interval using the standard deviation. And so my standard deviation is in cell B8. And so here I'm going to type in B8 or click it. I'll just click it. And so that's my standard deviation. And the size is how many measurements. The more measurements we have, the more confidence we can have in that average. Here we only have 3. 3 is actually a common size. Do you know why?
Isn't it like the best amount of trials to do based on like
Yeah, right. 3 is the best because it gives you the biggest payout for the fewest number of trials. So, for example, if you did only 1, then the confidence interval is huge and it's imprecise. You don't know. If you do 2, it's a dramatic improvement. If you do 3, it's a great improvement. If you do 4, it's a little improvement. 5, a little improvement. And so it's diminishing. It's like the law of diminishing returns. It gets smaller and smaller. So the difference between doing 1,000 trials and 1,001 trials is minuscule, and versus the difference between 1 and 2 is huge. And so 3 is about it. But if it's easy to do, then you should do as many as you can get. If you can get 1,000 trials, that's better. Do it. But if it takes you a lot of time, then 3 is the best compromise. And so we'll go with 3 here. Click OK. So our 95% this is going to be the range. So it's going to be our average plus or minus 1.2. So what we have is we have 95% confidence that the true value is going to be between, 1 minus 1.2 is going to be a negative 0.2, which you can't go negative. So it's going to go from 0 to 2.2. So we are going to assume that the density of waters with 95% is going to be between 0 and 2.2. That's a huge range, right? Versus this. So I'm just going to copy this and paste it over here. So copy, paste. That way I'm not going to input it. Let's just copy these 3 and paste it over here. Whereas over here, it's much narrower. And so what we say is we have 95% confidence that the true density is between 0.8 and 1.2 based on our data. And so student B has much better data than student A based on the confidence interval. We'd see this. So we can't have much confidence in student A, but we can have a lot more confidence in student B. Okay, are there any questions on this? I'll give the equations for this later, but I'm going to stop talking now. And the Excel calculation is pretty straightforward. So why don't you go ahead and go out to the computer lab, and we're going to work up our data together.